The objective of this lab is to apply the principles of interferometry to the task of angle measurement. Using the Hewlett-Packard laser, an angular interferometer, and an angular reflector, yaw and pitch errors will be measured for a diamond turning machine's z-axis slide. In earlier labs, we discussed straightness of motion measurement for translating carriage. We noted that the ideal carriage experienced motion in only one direction, the direction along the axis of intended carriage travel. Such an ideal system would be characterized as having 1 degree of freedom. We quickly added that actual carriages exhibit unwanted lateral motion, thereby introducing position error. For example, a carriage designed to move only along the x-axis will in reality also translate in the y and z directions. In addition to these translational errors, angular errors exist which can also give rise to additional positioning errors. These angular errors, yaw, pitch, and roll, are the angular or rotational degrees of freedom associated with an axis of motion. Therefore, for an actual system, there are 6 degrees of freedom for each axis of motion, 3 translational and 3 rotational. For the orthogonal reference system shown, yawing of the x-axis carriage is defined as rotation of the carriage about the y-axis. Rolling of the x-axis carriage occurs when the carriage rotates about the x-axis. Pitching of the x-axis carriage is rotation of the carriage about the z-axis. The effects of these rotational errors can be more difficult to conceive than the translational errors, largely due to the fact that these types of positioning errors occur when the angles combine with offsets. This point can be illustrated with the following example. Suppose that the position of the center of the carriage is our only concern. Furthermore, assume that there are no translation errors and that the yaw, pitch, and roll of the carriage occur about the non-rotating axis through the center of the carriage. With these conditions, these angular errors create no positioning problems for the center of the carriage because there are no offsets on which the angles can work. However, if an x-axis offset exists, yaw and pitch positioning errors occur for that x-axis carriage. The yaw positioning error has a z-axis component and an x-axis component. The magnitude of the z-axis component is equal to the product of the offset distance and the sine of the yaw angle. The magnitude of the x-axis component is equal to the offset distance times the quantity 1 minus the cosine of the yaw angle. Given that these angles are typically very small and that the cosine of a very small angle is nearly 1, the x-axis component is considered a second-order error and is often neglected. The pitch positioning error has a y-axis component and an x-axis component. The magnitude of the y-axis component is equal to the product of the offset distance and the sine of the pitch angle. The magnitude of the x-axis component is equal to the offset distance times the quantity 1 minus the cosine of the pitch angle. As stated earlier, given that these angles are typically very small and that the cosine of a very small angle is nearly 1, the x-axis component is considered a second-order error and is often neglected. If a y-axis offset exists, pitch and roll positioning errors occur for that x-axis carriage. The pitch positioning error has an x-axis component of magnitude equal to the product of the offset distance and the sine of the pitch angle, and a usually negligible y-axis component, the magnitude of which is equal to the offset distance times the quantity 1 minus the cosine of the pitch angle. Similarly, the roll positioning error has a z-axis component of magnitude equal to the product of the offset distance times the sine of the roll angle, and a y-axis component with a magnitude equal to the offset distance times the quantity 1 minus the cosine of the roll angle, again, which is often ignored. If a z-axis offset exists, yaw and roll positioning errors occur for that x-axis carriage. The yaw positioning error has an x-axis component whose magnitude is equal to the product of the offset distance and the sine of the yaw angle, and a usually negligible z-axis component of magnitude equal to the offset distance times the quantity 1 minus the cosine of the yaw angle. Similarly, the roll positioning error has a y-axis component with the magnitude equal to the product of the offset distance and the sine of the roll angle, and a z-axis component with a magnitude equal to the offset distance times the quantity 1 minus the cosine of the roll angle, which again is often ignored. As we have just seen, yaw, pitch, and roll errors can have significant impacts on the accuracy of a machine. In the design of this diamond turning machine, or DTM, many of the effects of these angular errors have been minimized. For example, the laser interferometer optics are located at the height of the tool and spindle center line, thus minimizing the Abbey offset between the measurement axis and the axis of motion. Note that this arrangement does not prevent the carriage from pitching, but simply provides a sort of built-in compensation for the effects of that pitching. In most cases, design constraints make it impossible to eliminate all offsets. In this DTM, the laser interferometer optics are located off-center of the spindle in the x-axis direction. With this x-axis offset, a yaw angle would cause the measured z-axis position and the actual z-axis position of the spindle center to disagree by an amount equal to the product of the offset and the sine of the yaw angle. But note that even for an Abbey offset of 0, z-axis error would result when the tool moved radially away from the center of the workpiece. From these brief examples, one can already sense the complex nature of machine design when viewed from a metrologist's perspective. In today's lab, we will use an angular interferometer system to measure the yaw of this DTM z-axis. Specifically, we will use a Hewlett-Packard laser head with a measurement display, an angular interferometer, an angular reflector, and the HP laser tripod. The measurement range of this system is plus or minus 1 degree with a maximum resolution of 1/10 of an arc second. From the first lab, recall the operation of a linear interferometer. The light from the laser head enters a linear interferometer where the two differently polarized frequency components are separated into a reference beam and a measurement beam. The measurement beam is aligned with a moving retroreflector, and the reference beam is aligned with a stationary retroreflector. Distance measurements are made by sensing the frequency change caused by the motion of the measurement retroreflector. As you probably recall, this frequency change is known as the Doppler effect. With an angular interferometer, the operation is only slightly different. The angular interferometer is essentially a linear interferometer with a built-in beam bender so that the separated reference and measurement beams emerge from the interferometer as parallel beams. Unlike the linear interferometer, the measurement and reference beams are each directed toward the moving angular reflector. The angular reflector consists of two retroreflectors positioned a specified distance apart. In essence, there is no reference beam, but rather two measurement beams. If the movement of the angular reflector is purely translational, each retroreflector will have the same velocity, the two frequency-shifted components will be approximately equal, and the changes in the lengths of the two measurement paths will be the same. If the movement is rotational or has some rotational component, the changes in the lengths of the measurement paths will be different because the velocities of the two retroreflectors will be different. From this velocity difference, there will be a difference in the Doppler shifted components from which the difference in the length changes can be determined. With a knowledge of the difference in length changes and the retroreflector separation, the angular orientation of the angular reflector can then be determined. Before setting up the equipment, these points should be stressed. Although the output of this laser is less than 1 milliwatt, no one should look into the laser beam or stare at its reflection. Skin damage is not a danger, but eye damage could result from carelessness or improper use. Furthermore, always use extreme care when handling the optics, paying special attention to avoid touching the optical surfaces. In preparation for these measurements, the spindle's vacuum chuck is removed and a special mounting plate is attached to the housing of the spindle's air bearing. Using double-sided adhesive tape, the angular reflector is mounted to the angle support on the mounting plate. Note that the reflector is positioned so that the retroreflectors are facing out, that is, away from the spindle. Here, the reflector is horizontally positioned for making yaw measurements. If pitch measurements were being performed, the reflector would be positioned vertically. A fixture for holding the angular interferometer is mounted to the x-axis slide. The angular interferometer is secured to the fixture's angle support so that the interferometer faces the angular reflector. Obviously, the interferometer will also be horizontal for yaw measurements or vertical for pitch measurements. In this measurement, the reflector will move with the z-axis slide and the interferometer will remain stationary on the x-axis slide. As you recall from an earlier lab, the laser beam enters the interferometer first. Therefore, with respect to the beam path, the interferometer must lie between the laser and the reflector. Note that two ports are provided on the interferometer to allow inline or right angle measurements. The interferometer and reflector are aligned with the axes of motion in both the horizontal and vertical planes. Here, the interferometer is being aligned horizontally with the x-axis. The probe of an electronic indicator gauge is set up to traverse along the surface of the optic housing in the x direction. The optic housing provides a good reference since the optical elements have been assembled in the housing to within plus or minus 2 degrees. Note the orientation of the stylus axis with the transverse direction. The variation in the gauge reading is monitored as the stylus is traversed. Based on the amount of tilt indicated by the display readings, the position of the interferometer is corrected by adjusting the support bracket. After both the reflector and the interferometer have been aligned with the machine axis, the laser head is mounted to the tripod. Using the tripod adjustments, the assembly is nominally aligned with the reflector and interferometer. Note that the laser head and tripod are positioned as close as possible to the DTM in order to minimize the effects of air path fluctuations. When the tripod position has been established, the laser head is leveled by adjusting the lengths of the tripod legs until the bubble level is centered. Connect one end of the interconnection cable to the laser head and the other end to the laser source socket on the rear of the measurement display. Connect the display's power cable to a 110-volt AC receptacle. Power up the display by pressing the rocker switch to the on position. The laser system requires 10 minutes for its initiation and warm-up routine. On the laser head, check to see that the ready indicator is lighted. Next, ensure that the laser head's turret ring is set to Other. Recall that the laser beam exits the top port on the laser head and that the returning beam enters the bottom port. Rotate the small beam aperture into place over the top port and rotate the target into place over the bottom port. Press the angle key to select angular measurement mode. To obtain greater resolution in the values displayed, press 1, then press the resolution key. This will allow measurement in tenths of an arc second. To return to 1 arc second resolution, press 0, then resolution. The display is zeroed by pressing the reset key. This can be done only after the laser head has been aligned with the optics. To align the optics, a target is placed on the entry-exit port of the angular interferometer such that its crosshairs are at the bottom and its hole is at the top.